Okay, now let us talk about utility theory. Now, why is it the basics of game theory? See? Because game theory talks about how agents, rational agents, or boundedly rational, so agents who have, like people, only a bounded ability to choose what they do. So we look at how they act. But they act, we assume, based on what they want. And utility theory exactly studies what they want. And let me just give you a little spoiler. Till now, scientists, usually psychologists or or behavioral economists, don't know exactly what people want. So utility theory is still an open question. But we are going to assume the classical approach of von Neumann and Morgenstern. And okay, let us talk about the following. So the approach of von Neumann and Morgenstern is called the linear utility theory, linear expectation. And basically, it assumes that the utility from a given situation can be expressed by simply a number, a function which gives number to any situation. So if I choose 2, Jack chooses 3, and John chooses 5, then in this abstract game, I get that pair, Jack gets this pair, and John gets some other pair. So we assume that there is a utility theory, a utility function, which represents what happens, and more, it's important that when you have a choice between lotteries, then you can look only at the expected value of this function. So it's a very useful thing, it's a very simple thing. Now in reality we know that we cannot just look at the expected value, and there is a famous prospect theory by Kahneman and Tversky, for which Kahneman got Nobel Prize and simply Tversky had died before that. And even that theory, as Kahneman writes in his own book, is not perfect. But we are going still to use the famous theory of von Neumann and Morgenstern, which is definitely not always what people do, but it's definitely good enough for many things. Okay, so let us now write it formally. So a lottery a lottery is a possible outcome, abstractly saying, is a probabilistic outcome in the following sense. You have the outcome O1 with probability P1, outcome O2 with probability P2, so forth. Let's assume a finite number of outcomes, and so outcome OM with probability PM. And we write this, outcomes are not numbers. So we are going to write something symbolically, please take heed. So L is this lottery, and we write the lottery as a sum of the outcomes weighted by the probability. And let's say, outcome Pi, Qi, I goes from 1 to M. Since again, these are not numbers, it's just a symbolic notation. So that's a lottery is a certain situation when you know that you get this with probability this, Q2 with probability P2, NQM is probability PM. That's a definition of lottery, of what can happen. Now, the probabilities Pi have to be a probability distribution. And that formally means that they are all non-negative. And since something has to happen, the sum of those Pi's is exactly 1. So Pi, when I goes from 1 to m, is exactly 1. Okay. Next, denote the preferences of the agents. Let's look at a certain agent. By this notion, if what is in the left is preferred to what is in the right, so it's kind of a curly larger, bigger. This is curly bigger or equal. This is curly equal, curly smaller, and curly smaller and equal. So you can say, for example, that from the point of view of some agent, outcome O1 is strictly preferred to outcome O2, while outcome O2 is not better than outcome O3. For example. So these are the notation. This is still just a notation, and we are not going to work with such a complicated notation. As I said, we are going to move to a function. I'm just now explaining why, at least given the assumptions of von Neumann Morgenstern, which we are going to take, why we will allow ourselves to move to numbers. So the basic theorem of von Neumann Morgenstern, which allows us to do that, is as follows. Consider, okay, let me write it down. I apologize for the quality of writing. So the theorem is as follows. Consider a finite set of outcomes, a finite set, references which are close under mixing probability. So consider a set of outcomes which is finite, references which are closed under mixing probability. Preferences, well, let me write it fully, close under mixing probability, which means that if you have two lotteries, two things you get, L1 and L2 in this set L, capital N, then for each probability P between 0 and 1, a combination, a convex combination of the form P take L1 plus, remember plus is symbolic because those are L1 and L2 are not numbers. They have not yet passed to functions which give real numbers. So PL1 plus, plus 1 minus P. L2 will also be in L. So by combining what you get, so let's say I get $100 with probability 1/3 and $1,000 with probability 0.7. And there is another option, I get something else. And if I combine those, this is also something in this set L. So set L is rich enough. It's important for us that set L is rich enough. In particular, we can combine any two lotteries with any real number between 0 and 1. So it has to be closed like that. We also assume something which is also natural, reducibility, that you can always look at the basic outcomes, even if you have combination of many lotteries, because lottery is a combination of outcomes and we combine. So n reducible. What it means is that let me think how to write it. So if you have a lottery, if you have PILI, so you have L1 with probability P1, L2 with probability P2, and so on till Lm with probability Pn. And you have another lottery. You have QILI with other probabilities. And then you combine those lotteries. You add another level of probabilistics. You had another level. So you take the first lottery with probability alpha. The second lottery is probability, well, it has to be 1 minus alpha, sorry. Then the result is equally good for us. And I have to write that. As if you just open the braces, so to speak. So if you just speak about alpha from I from 1 to m, you have alpha p I plus 1 minus alpha qi. So we can always get back to the more basic lotteries. We can always eventually talk in the terms of basic outcomes. So that's another necessary thing we need to work with lotteries. And then the theorem says as follows. Then there exists a function, a utility function that we want. So it gives to each outcome a real number. It tells how good it is for us. And then we can basically combine lotteries by lotteries by calculating the value of this function. So such that the value of the lottery PILI is not more than the value of the lottery with QIs if and only if we can just combine, and here these are numbers, so we just look at the function of each one of the LIs, assuming that LIs are basic, so assume that it should be OIs. OIs are basic outcomes. So we basically calculate the functions of the basic outcomes, and then we just combine the functions with the weights PI. And then we choose which expression is larger. That what means to say that the function represents our preferences. Okay. So then there exists a function which represents our preferences, exactly what we want. But it does not always exist. It exists if and only if The following set of axioms holds. And as I said, we are going to assume that holds. So now let us write. So this important theme takes place if and only if the following set of axioms takes place. First of all, the order of preference is completeness. It means that any two outcomes can be compared. So, no, it's not Q, O. O1 is either less good than O2 or it's better than O2. Better or equal. You can always compare. Intuitively speaking, of course, you understand that if you want to be able to represent something by number, it means that probably we need to have all the number means that you can always compare stuff. So I'm just giving you intuition, of course. That's not a proof. I'm just formulating the theorem and giving you the intuition for the conditions. Another one is it has to be transitive. Again, when you have numerical comparison, it's natural that you have transitivity. And transitivity means that if you have Q1, which is at least as good as Q2, and Q2 at least as good as Q3, it means that Q1 is at least as good as Q3. So you can kind of transit from Q1 being at least as good as Q2 and Q2 being at least as good as Q3 to compare Q1 and Q3. The third axiom is continuity. So that, again, when you talk about real numbers, it will now see, it will intuitively require some kind of continuity. What we mean here by continuity is the following. If you have three preferences, L1, L2, and L3, L1 is less preferred than L2, which is less preferred than L3, then there exists P between 0 and 1 such that L2 can be obtained the same as combining L1 and L3 with those weights. So PL1 plus 1 minus PL3. And the last requirement is independent. Well, that's in general a very natural requirement. It's just interesting that it does not happen in real life. But we assume that. So independence basically means that if independence is exactly what we don't have, but actually you can see why we don't have it, because in real life people are extremely context dependent, so I can desire something more or less based on what I ate for breakfast. That's actually natural that people are not independent, but when you think of what we should be like, in theory, we should be like that. If L1 is less preferred than L2, then for each P between 0 and 1, if we combine L1 with some other option L3, with P and 1 minus P, so instead of saying, okay, you just get this $100, you also say that, okay, you just get them with some probability, and with another probability you go to jail. L3 is going to jail. You just add something which is kind of new. then it's going to be at least as good as if you combine L2 with the same probability with L3. So if L1 was not as good as L2, then after giving them some extra thing in the same way, you still say that what you had with L1 is not as good as what you had with L2. It is kind of something we would expect to have for very, very rational creatures, but we are not rational, so as I said, it does not happen. But the theorem says that if all those four kind of intuitively holding properties hold, then you have this function which we can use instead of saying who wants what. We can just look at this function. And also there is an interesting thing that if such a function exists, if it's unique up to a positive linear transformation. So that's also probably something helpful if such a function from a set of outcomes to real numbers which does whatever we want exists, then unique up to positive linear transformation. Wow, that looks ugly, but that's not because the theorem is beautiful, it's just my writing which is ugly. Okay, well, it's also clear that you need to have some slack, because if you just want to compare, you can always say, I just add 100 to both sides, it will be the same order. So, of course, you need to have some slack, but the statement that it is unique after a positive linear transformation says that it's not something crucial. Okay, so by now we just have said that we are going to look at games where utilities, we just give a function of defines what we want. We are not going to speak about some preference order, some abstract preference order. We are going to speak about functions, which is much more convenient. It's questionable whether it's what happens in real life, but that's another thing. We also assume that everyone is infinitely rational. So we also assume that everyone exactly does the optimum given the knowledge of that person. Assume everyone is infinitely rational. In real life, it's not the case that people are not, and even corporations are not infinitely rational. And the preferences are not so nicely expressed by some linear, but some function which you can just combine linearly based on the probabilities. You have people who are risk averse. You have people who are, who are risk loving or risk seeking. And as Kahneman and Tversky showed that the question whether someone is risk averse or risk seeking often depends on whether you are winning or losing and how much you are winning or losing. So it's quite complicated. And even the prospect theory that they suggested to replace von Neumann and Morgenstern's theory does not completely answer this question, but at least within some reasonable first approximation, we have the right to use utility functions, and that's what we are going to do. Now that we are going to talk finally about non-cooperative game theory.